Hello, this is a video for 6.3a conditional probability, and in this section we will not be using a formula. We were going to be figuring out conditional probability in context. So let's go ahead and get started. We've got 6 pieces of paper numbered 1 through 6 placed in a bag. You draw 2 pieces of paper one at a time without replacing the first. So can we make a tree diagram for this situation? Absolutely we can. Should we do that? No, because we have a lot, actually limited space here. So no, we don't have enough room. That doesn't mean that we can't, it just means that we don't have a lot of room here. Sometimes it's better just to kind of think about it in our head. So what we're going to do is we are going to write the first part and then we're going to match with what our second could be. So our first draw could be 1. Now since I can't draw the number 1 twice, I can draw a 2, or I could draw a 3, or a 4, or a 5, or a 6. So that would be that first part right here, and then I would have 5 possibilities off of that, but we're not going to draw the tree diagram, we're just going to list the sample space instead. So instead of us drawing 1 the first time, we could draw a 2, and on the second draw I could have a 1. I cannot draw a 2 twice, so I'm going to skip 2, and I'm going to go with 3, 4, 5, and 6. So that would be the second branch of the tree diagram. Okay, what if I had a 3? And if you notice the first 2, I branched off 5 times. I'm going to do the same thing with 3. I'm going to do the same thing with 4 and 5. Yep, I can't forget 6. I almost forgot 6. Okay, so each one of those is going to have 5 branches as long as I don't repeat the number. So I'm going to have to skip 3. And then on 4s, everything but 2 4s. So I'm going to skip 4, go to 5. Skip the 5, go to 6. And on the last one, I have everything but a 6. So that is my sample space. Notice that I had 1, 2, 3, 4, 5, 6 possibilities for the first draw, and then for the second draw I have only 5 because I can't draw the same number twice, which should give me 30 total outcomes. You always want to do that because if you're going to be asked questions about probability, then that's going to be your denominator. Okay, so what's the probability that you draw 2 odd numbers? So I'm going to highlight everything that would be 2 odd numbers. So odd, odd, and then this isn't going to work because that's even. That's even, odd, odd, and then that's even. Okay, so it looks like I only have 6 odd. So 6 that are 2 odd numbers out of a total of 30 total, and then 6 out of 30 is equal to 0.2 or 20%. So I have a 20% probability that I'm going to draw 2 odd numbers based on that sample space. So this next one is a little bit different. It says when the first number you draw is odd, what is the probability that the second number you draw is also odd? So this is similar to what we just did, but it is slightly different. So let me highlight this. When the first number you draw is odd. So what I'm going to do in blue is I'm going to circle everything in the sample space with a first number that is odd. I am boxing in all of the sample space with the first number odd. Now what that's done is that limited my total outcomes. So I no longer have 30 total outcomes, I only have 15. If you count everything in here, I only have 15 possibilities. So when I do the second part, what's the probability that the second number is also odd? What you're going to do is you're going to look only in the things that I've boxed in. So second number also odd, it's going to be all of these right here. So I've got 6. So the second is odd. And then I only have 15 where the first is odd. Okay, so 6 out of 15, that's equal to 0.4 or 40%. So there is definitely a difference in probability according to the way the wording is. So what is the difference in the probability in the two previous examples? Well, it looks like in the second example, we are limiting our sample space. So the probability in part B, that's called conditional probability. So when it says conditional probability, this part right here in blue, that is our condition. So how would you define conditional probability? It's going to be the probability of an event given that another event has occurred. Okay, so once again, conditional probability is going to be the probability of an event given that something else has occurred, and I call that your condition. And you need to be able to find that condition whether it uses the word given or not. So the notation, or the way that we write conditional probability, is very important. So right here it talks about it. The probability that event B occurs given that event A has occurred, that's called conditional probability, and it is written like this right here. So I'm going to zoom in on this for a second. So we're basically talking about the probability of event B occurring considering, so this is the condition, that A has already occurred. So it's really important that you read this notation in such a way that you're finding the probability of this first event given that A has already occurred. So whatever appears in that second part after the vertical line is called your condition. Now we've already done stuff like this in this chapter. That just means that A and B occur at the same time. So you're going to have to get used to this, which means conditional probability. And remember, the second thing is your condition. So you're going to find the probability of B given that A has already occurred. So we're going to practice that a little bit using the sample space we've already written down. Now this new conditional notation can be intimidating sometimes, so the way that I got better at it is I wrote everything out in words first. So if you look, event A means that the first number is divisible by 3. So what I'm going to do is I'm going to replace A and I'm going to replace B, which happens to be the second number is greater than 2. I'm going to just rewrite this in words, okay? So we're going to say the probability of B, so the second number is greater than 2. So I'm using symbols here to help me write it out. And then I'm putting my vertical line, and then my condition is the fact that I have a first number divisible by 3. So this is my condition. And you are going to limit your sample space based on that condition. So what I'm going to do is I'm going to go up here and I'm going to circle everything that has a first number divisible by 3. So first number divisible by 3. Divisible by 3 means that 3 will divide into it evenly. So I've got all 5 of those. No, not that one. This one. So how many do I have with a first number divisible by 3? I have 5, 6, 7, 8, 9, 10. So I've got 10 total. That is my condition. So whenever I figure out the probability of this, I have to divide it by 10, which is the condition. So how many out of those 10 that I circled have a second number greater than 2. So I'm going to change colors and I'm going to circle these. So this one's greater than 2, and I'm looking for the second number greater than 2. Okay, looks like I've got 6 of these out of a total of 10. So 6 out of 10 reduces to 3 out of 5, which is 0.6 or 60%. So if you have a condition, you have to limit your sample space, which changes the number in your denominator. Okay, now the second one is not conditional. You need to find the numbers that satisfy both of those at the same time. So I have to have a first number divisible by 3, and I have to have a second number greater than 2. So I already have those that are circled right here. So these are divisible by 3 and they're greater than 2. So I still have 6, but I don't have a condition to satisfy. So I had 30 original, so 6 A and B, 30 total. That's going to give me 0.2 or 20%. Okay, and then the last one is just the probability of the first thing occurring, and A was the first number is divisible by 3. I have no condition. I just need to figure out how many have the first number divisible by 3. Well, those are all the ones that were circled in blue, so I have a total of 10 that are divisible by 3, or the first number is divisible by 3, divided by the original total, which is 30. So it's 1/3 or 0.33, that's rounded by the way, or 33%. Okay, let's look at the back of our notes. So one more time, we have the conditional probability, and I'm going to remind you that the second thing right here is your condition, which will limit your sample space. See how I put the number of outcomes of your condition? But when you're going to find the probability, it would be outcome of both events. Now, since you've already limited your condition, that top number is going to be pretty obvious, especially if it's in a Venn diagram or if it's in a two-way table. Or you could just simply look at your sample space, which is what we're about to do. So this example says a family has 2 dogs and 2 cats. They randomly select a pet to get brushed, and then they randomly select a different pet to get a treat. So I'm going to go ahead and start this out. I'm going to say brushed. Now, we're not going to be able to be brushed and get a treat at the same time, so we're going to have to pick a different animal to get a treat. So we do have a condition. Find the probability that they select a cat to get a treat, given, all right, so here's our condition, given that they selected a dog. So that dog is going to get brushed. So when I do my tree diagram, I'm only going to start with dogs because I'm trying to find the probability given that a dog got brushed. So I've got 2 dogs. So I'm going to say dog number 1 and dog number 2. Now, like I said before, this has a condition, so I'm only doing a partial tree diagram. So the dog is getting brushed. Now, the second animal cannot be repeated. So I cannot do dog number 1 for a brush and a treat. So I'm going to do dog number 2, and then I have 2 cats, cat 1 and cat 2. Same thing here. I can't repeat dog number 2, so that might be dog number 1, and cat 2. So it says find the probability that they select a cat to get a treat. So how many of these have a cat get a treat? 1, 2, 3, 4. So I have 4 out of a total of 1, 2, 3, 4, 5, 6, which is, I should simplify. So 2/3 or 67%. Okay, this one says write using probability notation and then find the probability. Well, I just did that, so let's do the notation though. I got ahead of myself, sorry. So we're going to do the probability of, let's see, so they select a cat. So a cat gets a treat given, so that's what that line means, given that we have a dog get brushed. So that means that my probability is going to be the probability of a cat treat and dog brush, and that's going to be divided by the probability of just the dog getting brushed. So that's going to be 2 out of 3, or 4 out of 6, which was 2/3, or the 67%. All right, so these examples are in words and they are in that conditional probability notation. You need to understand that defective is going to be your condition, and in part B, non-defective is your condition. And this is a two-way table. So if you're doing conditional probability in a two-way table, it's actually very easy. You don't have to create a sample space, and I will show you how to do it. Okay, so let's look at defective as being your condition. So look at the defective row right here. So I'm just going to circle everything in this defective row right here. And then within that defective row, so me circling that limited your sample space. So we're not going to look at the whole table anymore. So how many passed given that you're looking at only the defective parts? So how many passed? We have 3. So I'm going to do 3 out of how many were defective? 3 plus 36. We're going to do a little bit of math here, which is 1 out of 13. And if you're working problems in Delta Math, then you can just leave it a fraction. Okay, let's look at this one. This one says non-defective, so let me erase it. And I'm going to look at just the non-defective section. And it wants me to figure out the probability of failure given that we're only looking at the non-defective parts. So what fails? We have 11, but then in the non-defective section, we have 450 plus 11. So my final answer is going to be 11 out of 461. So you might have to add the row or the column depending on the question. Okay, so we're kind of at the end of our notes, and I want you to just pause the video. I want you to read both examples and just see how you do. Now the first one's a word problem. You can create a sample space for that one. And on the second one, just focus on the condition and find the probability from that. And when you're ready, go ahead and just push play and let's see how you did. Okay, so on this first one, what you could do is you can make a complete tree diagram, but I'm not going to do that because I'm limited. Let's see if we can find that limitation here, or that condition. It says, given that you were served a hot option first. Well, how many hot options do we have? We have 2. So for my first choice, I'm only going to have option 1 or option 2 for that hot option, okay? Now, on that second choice, I'm not going to repeat the hot option 1 or 2. So I've got 3 different cold foods. So I'm going to do 1, 2, 3. So cold 1, cold 2, cold 3, but I could be served the second hot option. I just don't want to repeat the same food again. So I had 4 choices here. I'm going to have 4 here again. So cold 1, cold 2, cold 3, and then hot option number 1. So here I've got 8 because I've got 2 here times 4. So I have a total of 8 options because instead of it being like the whole tree diagram, I was limited to just a hot option first. Okay, then it says find the probability that you're served a cold option second. So how many of these have a cold option in the second choice? 1, 2, 3, 4, 5, 6. So I have 6 out of 8, which is 3/4 or 0.75 or 75%. So if it doesn't have a two-way table, you can create a sample space that is a limited one, or a tree diagram that is limited, and do your probability from that. Okay, on this second one, what we're going to do is we're going to focus on this condition here. This is non-defective. So we're going to look at total non-defective. We're looking for failures So that would be 9 out of, now remember you're only looking at this row, so if you add 208 plus 9, you get a total of 217. And then failure, this is actually a column, so I'm only going to look at failure this time, and I need to find the ones that are defective that failed. So it would be 24 defective out a total of, so you've got to add these two together, that would be 33. And then of course simplify it with your calculators, and then that would reduce to 8 out of 11. All right, that's pretty much it for the conditional probability without using a formula. So just let me know if you have any questions. Go ahead and get started on your homework problems, and have a great day.